What's up, Dr. D? My name is Kyle Wicks, and this is my X-ray circuit presentation. Okay, so today we're going to be talking about this image as well as another one. But before we even get started talking about that, I just want to mention that even though I'm going to be talking about things in steps here and segregating certain areas of this, everything is going to be happening essentially simultaneously. This is because electricity moves so fast that all of these things are going to be happening pretty much at the same time. Okay, so before we even get into the X-ray room or talk about the X-ray circuit itself, we need to talk about the electricity that comes into the building. So electricity from the power company is supplied at 220 volts, 220 volts. And that is way too high a voltage to use for most things. So outside of residential buildings, commercial buildings, or even like most hospitals, there will be a step-down transformer that brings the 220 volts down to 110 volts, 60 hertz. So then this 110 volts, 60 hertz is what we actually use within the X-ray machine. The X-ray machine is going to be, or this X-ray circuit diagram is going to be segregated into a few different parts. So firstly, the top and bottom are going to be separated. The top side is going to be the anode circuit, and the bottom side is going to be the filament circuit. Within the top side, we're going to have the low voltage or primary circuit on the left side, and then the high voltage or secondary circuit on the right side. And then the bottom side, that's actually going to be switched. So we're going to have a higher voltage side on the left, and then a lower voltage side on the right. Okay, so let's talk about the low voltage or primary circuit of the anode side. All right, so this blue line here, or this blue highlight here, is the path of electricity, essentially. This is the entirety of the low voltage side of the anode circuit, okay? There are a few things of note in here. First of all, let's talk about the kilovolt meter. The kilovolt meter will read the settings that we put into our control panel, or our technique that we use for our exposure. And in this case, I chose 100 kVp, 60 mA at half a second. So it'll read that 100 kVp and send that information over to your auto transformer, okay? Your auto transformer will use a moving selector hand that will line up with one of these dots, and each one of these dots will represent a different kVp amount. So for demonstration purposes, let's say that this center dot here is 100 kVp. So like 20, 40, 60, 80, 100, 120, 140, etc. Okay, and then another huge thing to note with this auto transformer is that it uses induction. There's actually no connection here. There's no wire. So it uses induction, which is the process of electricity moving from one object to another without actually touching, without the objects touching themselves. So the electricity moves from here to here without touching, moves up towards here, and then we have our exposure switch and our timer. And our exposure switch is what actually starts our exposure. So if our main switch here, if that is used to start our warm-up procedure and get electricity into our machine, then the exposure switch is what starts our exposure. It does this essentially by using a drawbridge type mechanism. When the switch is depressed, the drawbridge lowers and connects the circuit. And then when the switch is raised, the drawbridge raises and the circuit breaks. There's no contact anymore. So one thing that we need to know about the exposure switch is that we need to follow the timer. We need to hold that exposure switch for exactly as long as our setting says. So if our setting says half a second, we need to hold that for half a second until we hear a beep and see a light from our timer. There are certain timers that are called automatic exposure control timers, that automatically terminate the exposure when their desired setting is reached. However, it's still good practice to hold that switch down until it beeps, until it shows your light. And then like I mentioned earlier, the main switch also does start the warm-up procedure, which is necessary to prevent breaking from a sudden heating or cooling of certain parts of the X-ray circuit. Okay, so now that we talked about most of the main components of the actual low voltage or primary circuit of the anode side, how do we actually get to the high voltage side? Well, we go through what's called a step-up transformer. A step-up transformer uses a lower amount of coils on the one side, the primary side, and a higher amount of coils on the secondary side. This causes a raise in voltage. So in this case, we go from 110 volts all the way to 10,000 volts. Crazy, huh? So that 10,000 volts isn't going to be released in all, like in one burst though, which is important to note. It's going to be stored in capacitors and slowly trickle through in what's called a falling load type generator. Okay? So now that we established that this is going to be our high voltage side, and we're over here now, let's talk about some of the important parts of this side. Firstly, we have our MA meter. This MA meter, also called the mass meter, will read the product of your timer here and your filament ammeter here. We'll talk about this in a moment, but essentially all the filament ammeter and variable resistor are going to be doing is selecting your MA that you put in your technique inside your control panel. So it reads your timer and your filament ammeter to make sure that you have the right setting, and it also reads that 10,000 voltage to make sure that it's the proper amount. If either of those numbers were off, it would send all the current down to the ground and terminate the exposure. This little 3-4 lines here, it is the ground, and it gets rid of all the current. It would safely terminate the exposure. Okay, so now that we talked about the MA meter, let's talk about the actual path of the current over here. So it gets a little bit more complicated than the other sides, so let's try and go over this. Since it can only go in one direction past these diodes, and what are diodes, you might ask? Diodes are rectifiers that change the current from AC, or alternating current, to DC, to pulsating DC, or pulsating direct current. So we'll follow the orange line here first. Go over to the right, go up, go through to the diagonal to the left, and then you can only pass through the backs, or the side here that doesn't have the smaller portion of the triangle. Okay? So then we have to go through that side, over to the right, because we can't go this way, right? There's a block here. We cannot go left. We go over here to the right, we go into the actual X-ray tube on the anode side specifically, and then we'll come back out after completing the circuit inside the anode side. We'll come through this pink side, go over to the left, and then again, we can't go through this side, so we couldn't go up. We have to go over to the left, go diagonal up to the right, and go down and back through the coils over on this side, okay? Then after we go through the coils up to the top, we'll have the green line. Go over to the right, go down, diagonal up to the right, again, through the passable side of the diode, over into the X-ray tube on the anode side again. And then lastly, we'll have our blue line, which comes out from the anode side of the tube, over to the left, and then diagonal to the left, again through the passable side of the diode, over to the coils, okay? So it's a bit convoluted, but important thing to note here is that there's going to be 4 diodes, 4 points of rectification, and that you can only pass the diodes in one direction. Okay, so now let's talk about the actual filament circuit. The filament circuit is going to be a little bit more simple. So you see the path of the electricity here. The orange is going to be the path. But I'll go over some of the actual points of interest inside of this. So firstly is the filament ammeter. I mentioned this earlier, but all the filament ammeter does is it reads the setting that you put into the control panel, that 60 mA, and it'll send that information over to the variable resistor here. The variable resistor works just like the auto transformer, in that it is a dial or a hand that'll select a certain setting, and then through the use of induction, it'll transfer that current over to the corresponding setting that would mean 60 mA. So this will also be our third point of induction. So after that, it'll keep going through here. We'll talk about the step-down filament transformer in a moment here, but to complete the actual high voltage side of the filament circuit, it'll go back up towards the auto transformer. But because you don't want these wires to connect, which would cause inefficiencies, you need to go around them or use induction. So over here near the auto transformer, we actually use our fourth point of induction. Basically, we just want to avoid touching these wires together, so we use induction to cross this gap and then go up and back to our main switch, back to the start of the circuit. Okay, so that is the entirety of the high voltage side of the filament circuit, okay? Let's talk about the low voltage side. So we get to the low voltage side through a step-down filament transformer. And this is also our fifth point of induction. A step-down transformer is a transformer in which the first set of coils has more turns than the second set. So in this case, it goes from 110 volts all the way down to 5 to 15 volts and 3 to 5 amps. That's going to be a huge drop. But that's also going to be just enough voltage, just enough amps to heat up our filament enough, but without breaking it. Okay, so we have this lower ampage and voltage, and we want to get over to the X-ray tube now. So let's start talking about that. Okay, so this is our actual X-ray tube. Before we talk about the actual filament circuit, I want to mention the envelope. So the envelope is a Pyrex glass or metal cylinder-like container that maintains the vacuum inside the X-ray tube. And a vacuum is necessary because if there's any air molecules, the electrons moving at extremely high speeds could collide with them, and it'll cause inefficiencies in the X-ray production. Okay, so now that we established that we're in a vacuum, we're inside the envelope, let's talk about the actual filament. So we have that 5 to 15 volts, 3 to 5 amps, coming into our filament here, and our filament is made of a thoriated tungsten material, and that is because it is a high melting point and high vaporization, or difficulty to vaporize. So it is heated up using this 5 to 15 amps, 3 to 5 volts. 5 to 15 volts, 3 to 5 amps. And the whole point of that current is to heat it up. So you're getting that tungsten to 2,200 degrees Celsius. And the whole point of that is so that it starts thermionically emitting electrons. These thermionic electrons are what actually will be turned into your X-ray photons once it gets sent over to the anode. Okay, so those thermionic electrons will start to gather on the end of the filament here, and then the focusing cup, which is a negatively charged nickel part, will push together all of those electrons through the repulsion attraction law, and it'll make a very dense thermionic cloud of electrons that will eventually be sent over to your anode. So once you get the desired amount of electrons over there, like for example, if for this scan we'll say you needed 1,000 electrons. Once there's 1,000 electrons built up there, they will send over to the anode side, at which point they will bounce off the anode disc here and become X-rays. But if nothing were to be happening on the left side here, these electrons would immediately burn through that disc. They're so high energy and so high speed that even the highly heat resistant tungsten would be burned through in an instant. So before we move on to that left side, I just want to mention a couple weird phenomenons that happen. So there's something called the line focus principle, which is essentially that this angle here on the anode heel is what determines this angle and the size of this part here are what determine the actual size of your X-ray beam coming out, your actual effective focal spot. So because of the use of that line focus principle and the angle here, you also get something called the anode heel effect. The anode heel effect causes electrons to bounce off at unpredictable angles at times. So all these other electrons, all these other green spots are tube arcing, or electrons that get sent in random directions and end up on the actual inside of the envelope. So the vaporized tungsten, all these green spots, will start building up on the envelope and cause like glazing, or it makes it less clear, the glass on the envelope less clear, and it causes inefficiencies. So that is one of the biggest inefficiencies of an X-ray tube and one of the biggest cause for breakage over time. All right, so now let's talk about the left side over here. This whole left side will be the anode side, and it's going to be broken into a few different parts. So first, let's talk about the stator electromagnets. Basically, these electromagnets will cause this inside portion of the rotor here to rotate. It acts on this armature and these bearings here, and through the use of electromagnetism, it causes this entire thing to spin at 3,000 to 10,000 RPM. This entire disc will be spinning at 3,000 to 10,000 RPM, and that is essential for the heat dissipation that rotation provides. Because like I mentioned before, if nothing was happening over here, if no spinning was happening, it would burn straight through that anode heel, like instantly, super fast. And that is also one of the biggest breakage points of a X-ray tube, is a stator failure or just a rotation failure in general. Okay, so now let's bring it all together. We have the filament circuit over here getting that 5 to 15 volts, 3 to 5 amps, heating up in the filament, causing the thermionic emission, getting the thermionic cloud condensed by the focusing cup, hitting your desired amount of electrons, say 1,000 electrons, and then sending that over to the anode disk that's getting rotated through the stator electromagnets in the rotor. And then the I'm not sure if I mentioned this, but the actual anode disk will be made of a tungsten rhenium alloy, because it's the tungsten for its high atomic number, its high melting point, and then the rhenium for its elasticity. And then the rest of this, the neck here and then the back of the actual anode disc, will be made of a molybdenum base, and that's going to be a cheaper alternative that also has very high heat resistance. Okay, so sorry, we had the electrons thermionically emitting, and the cloud is produced. So then that entire cloud, once it reaches the amount of electrons needed, will be sent over to the rapidly rotating tungsten anode, and then that tungsten anode, or it'll reflect off of the tungsten anode, it'll bounce off of it and come out the window, and that'll become your actual X-ray beams. And once all of the electrons that were thermionically emitting, that were sitting on the filament here, are sent to the anode, that will be saturation current, when there are no more electrons to be sent towards the anode. So once all that happens, you got your electrons coming off of here, off of the anode heel. They become the X-ray photons, they are ionized, and they go towards the patient, hit the IR, and that's what captures your actual image. And that's my X-ray presentation. Peace out.